לא, היא אומרת שהחליבו אותו באיזה מגירה שם, לא מצאתי, אולי את יודעת איפה זה בדרך. כן, תביא, אני אתחיל. Alright. Okay. So, hi again. Let's start this week, second and final part, talking about the functional MRI and exciting things we can do with the Bolt signal. So, just to backtrace a bit, what we did last time is talk a bit about the experimental designs that we have. Okay, what kind of designs, what this design can tell us basically, when to use which design. Those were, I remind you, block designs, event-related design, each with its own plus and minuses. We talked a bit about processing, pre-processing, and I remind you that there's a whole series of algorithms that you apply on top of the signal you get. Right? Some of them are mandatory to be able to basically tease out the signal from noise. Others, like the co-registration or normalization, are some steps you have to do in order to localize your activation in space. Okay, so either relative to the take the Bolt activation, put it relative to the anatomical image that you have with the co-registration, and sometimes you want to normalize, so move all to one single space, standard space that you can then compare with other different subjects or other projects or research that you find in the literature. And sometimes you smooth the data, but in the end you have a bunch of processes you do here. So some of them, you, like I said, are mandatory here. Up until here, I would say up until motion correction, okay, and co-registration, you have to do some co-registration, and then these normalization and spatial smoothing depend on the type of analysis you want to do. If you want to do the analysis on each and every subject separately, or you do something on the group. So, and we'll get back to that later today. So today we're going to talk about the analysis part and the approaches you can take to investigate actually what's going on with the activation. We'll concentrate about on the general linear model, the GLM, which helps us to estimate the relative contribution, okay, of different conditions that we have to the overall signal that we get. We'll get to that in a second. But before that, I'm going to just mention two other approaches, and later another fourth approach that you can take. So there are many nuances and many different, sub-approaches and sub-approaches that you can apply when you try to analyze the Bolt signal. It all also, of course, depends on the design that you have. So before we go to the GLM, I just want to mention really briefly that you can take the raw signal data, basically the raw timeline. Okay, you have a timeline of I don't know. This is scans, so these are TRs. So let's say it's 2 seconds. So we have here 440 seconds. There's an activation timeline for each and every voxel in the brain. You can take this basic activation along the time series, and try to find some kind of, let's say, rules or behavior of the data. So you can do it in a very data-driven approach, like the ITA, okay? Try to put some algorithm to tease, let's say, the total signal with some kind of noisy combination, and you try to tease out, let's say, several key components, okay, that are independent from each other. We have the ITA, we have TCA, we have all kinds of algorithms, and don't tell you exactly, like looking at this, you don't understand exactly what this component represents, but putting this kind of, let's say the red or the blue component together with the literature, what you know about the brain, and together with the time points, you know what happened in your experiment at that time point. And this time point, you can understand maybe what these components represent. Okay, so this is one approach that you can do. For example, here, so you have, right, you have some kind of activity here. Can you tell me what that is? Yeah, you see that? Which area is that? The motor cortex. Okay, so you have some left and right motor cortex activation. You have some occipital activation. You have different activation. So if you see this component rise, you can start to understand. Of course, this is easy because we know that the motor cortex is here, so we can do this the other way around, right? We see the signal, we understand that something motor, but if, of course, when you research, you want to tease out something new in your data. So that's just one approach that you can take. You can also take, so this is, you have some activation during tasks. You tell the subject to do something, you have different time points doing different tasks, seeing different stimuli, and you can tease out the components. You can also do this during rest. And this is the idea behind functional connectivity, okay? Not to be confused with actual anatomical connectivity that you test with DTI. And the idea here is, this is usually some kind of supporting analysis, but again, the idea is taking the raw data. In this case, when someone is resting or not doing anything in particular in the MRI, okay, you put usually someone with their eyes closed or open for like 6-7 minutes. You just scan the brain, okay? There's some wandering thoughts, there's some, I don't know, whatever the person does inside the magnet. And then you can put a seed somewhere, okay, like a group of voxels. You have the average time course, okay? This is average time course. Let's say the green one is an average time course of a region in the right motor area. And in this case, when you have the seed, you check throughout the brain which voxels show considerable correlation between the timeline and your seed timeline, okay? And the idea is, in this case, so the right motor in this specific case, it correlates very well with the left motor area. And this is non-direct, okay, evidence for some kind of connectivity between these two parts, okay? The activity rises together, gets low together for, let's say, for 6 minutes. It says something about the connectivity. So it's not a direct measurement, but it is very, very, it's a nice way to show this, especially when you apply it, as it says, as some kind of supplementary analysis. So, for example, we'll see soon, we find some region that you say is, I don't know, it's usually typically associated with vision, with static images, right? And now you show in your research that it is also driven by some other cues, not static images, but some motion images or auditory images, auditory stimuli, okay? So you say that, and it's also nice if you also show that this region actually connects well with, I mean, let's say, if you're now claiming it has some motion sensitivity in that region, if it connects to the, I don't know, to the frontal eye field of the motor cortex, okay, you got a very nice supporting evidence. But again, I'm just presenting this to show you that you can do things with the raw signal. And these are just examples for typical networks that you see around the brain, okay, executive control, default mode network, which is very active when we're not doing some, not busy some external task or stimuli, auditory networks, sensimotor, and so on, okay? This is very useful too. Last, before we go to the GLM, you can again take this raw signal and try to again find some correlations. And I'm not going to go into the details here because we don't have time. But you can systematically map some region. Let's say move some stimulus around, okay, in your visual space, so it has some frequency. So that if a voxel I'll just show it briefly. If a voxel is sensitive, this is the quadrant, right? A voxel, the receptive field, or is sensitive to this location in space, and you systematically move some stimulus like this, all right, in a very orderly fashion. So you have some frequency. Every, I don't know, every 12 seconds, the stimulus will arrive here. So the corresponding activation pattern for that stimulus, for that voxel, if it really is sensitive to this area, will be something like this. Every 12 seconds, let's say that's 12 seconds, whenever I present the stimulus here, we see a rise and then a drop, okay? So this is 12 seconds. So you can really do a lot of things, and you can continue and model this. You can really do a lot of things, but just trying to describe and see the correlation within the signal and also the correlation between different voxels. Okay? Is that clear more or less? We're not going to dive into that. It's just I want you to be aware that doing the GLM, what we're going to do next, is not the only way to try to tease out signal from noise in the data. Okay. Having said that, let's dive into the classic way of doing things. And this is really a typical functional MRI. So this is some different ones last week. fMRI image or figure, right? You have some positive activation, the yellow one, some negative activation, which is the blue and green one. In this case, this is the FFA, so this region is sensitive to phases, and usually you'll see some kind of interpretation for this, saying again, like in this case, that this is the phase selective area, okay? So how do you reach that conclusion? So let's take a very simple task, but it can tell us some things about how we do this. And in this task, we present 5 different categories, okay? In this case, visual, it doesn't have to be visual, of animals, faces, hands, tools, scrums. Right? So what we have here is a color code of the timeline, basically according to which we can build our predictors, because this is what we designed. So we designed that in time point, I don't know, 4 here. We show an animal, and then after, let's say this is around 8 seconds or 10 seconds, we start showing faces. So what kind of design this is, by the way? Yeah, simple block design, right? You have like, this might be even TR. So this is TR. So this is 42 seconds. So you have here, this makes more sense. So we have here about 12 seconds or something like that of stimulation, or 16 seconds stimulation. And then you move around the different stimuli, and you can see that it's not, well, you see, yeah, in this case it's periodic. This is just an example. Usually it's not periodic. So we change we randomize the order of the blocks. Okay, and now you want to see you know, which part of the brain responds more to which category, let's say. And before I go to the next slide, so the last category there is scrambled image, or it's not scrambled, it's phase transform. You know why you use this kind of images? Think, maybe, yeah?
Control.
Yeah, control for what?
To subtract the signal from the other signal.
Yes, exactly. And more specifically, yeah?
Texture and color.
Yeah, exactly. More specifically, we want to have some kind of category that has the same low level, if we want to, it depends what we want to do, but if we want to find an area that is, you know, representing this bird, but not the actual low level feature, but the objects, okay, of the bird, or the object of the face, we want to control it with images that contain the same distribution of colors, contrast, stuff like that. To see what, if we subtract between the two, like you just said, we can see if there's some kind of signal that is left that is associated only with the object. Okay? So we usually will have one of these, and this is considered rest in some experiments. Okay. So for example, we want to see which areas of voxel respond more to faces than to hands. And let's say we have, I hope you see that, you have some time course. Of course, it's a bit noisy. And, well, you can see there's some kind of response um, for faces. So it looks like it's the right one. Okay, you see some kind of rise a bit after the faces start to appear. So you want to basically find, when you're looking in the brain, you want to find voxels that behave like this. So this is a timeline of a single voxel. So how do you approach that? What you do is try to fit a model that will explain as much variance as you can achieve, explain as much of the signal that you have. Okay? So the idea is that you have this kind of signal, and again, you know what is going on in every second because you designed the experiment. Now we want to find a linear combination, okay, of signal, and by signal I mean activation that can be explained by the difference of conditions that you present, okay? So some kind of change in activity that rises, for example, when faces appear, or rises when houses appear, and so on. So the idea of the general linear model is that we have some kind of linear combination that together can explain this varying signal with minimum deviation from the linear combination. Okay, so this should be as efficient as I can, so that the residual will be minimized. I'll explain it again over and over, so don't worry if you don't get it now, although it's pretty simple. So if you, for example, and you can model this, so if you have these gray epochs, mean some kind of condition, let's say faces, and this green epochs means houses, you assume that there is some response for each of one of these conditions, okay? And what do we know? Well, I don't know exactly if you talked with Aviv before, but we do know that when we model this, we assume some kind of canonical hemodynamic response function. What do I mean by that? Is that although in reality there is some difference between how the HRF or the bold response develops in different people and also different regions inside single brain. Okay. For modeling part, we assume that basically you have some kind of canonical HRF. So the same shape of HRF, okay, applies. Basically, what I'm saying that you assume that whenever you see one kind of stimulus and a different kind of stimulus, the brain as a mechanism or what you can measure works the same. I mean the logic of it. All right. So the logic of the hemodynamic response function. Okay. What happens when the blood flows and then it flows out? Or you assume that this is the same. So what is left to be changed here to get some kind of changing signal is the combinatorics of this, and this means the different weights or different amplitude of the response function, because that can change according to the stimulus that's given in different voxels. So if let's say a single voxel is more active for faces than the houses, so the shape of the HRF should be the same, but the amplitude of the HRF when I present faces should be, I don't know, 4 times than the amplitude when it's presented, being presented by houses, and the other way around when for the house sensitive voxel. So let's we'll talk a bit about it. So this is, I'm just going to transform it now because usually you do this in matrices, and in order to calculate it, you usually just flip it around. Okay, so now it's vertical, but it's a different notation describing the same thing. Let me, let me just show you how it looks usually in data, so we understand more what I'm talking about. So first of all, when I have an experiment, I have a certain model that serves as a predictor, okay? So I know that I have 6 blocks when I'm showing a neck here, for example. I know that the first block starts on this TR and ends in this TR, so this, in this kind of experiment, it's 4 TRs, okay, each block. And from that I can basically build a predictor for each one of the conditions. Here it is. For each one of the conditions. And the predictor is just some kind of boxcar or very simple binary condition, okay, 1 or 0. So if this is the timeline, I have at 21, let's say this is 21, I have here something like that, and then I have at 53, let's say this is 53, and then at 77, and so on, okay? 53, and I'll have a different one for the faces. I don't have here. Oh, I do. So for the faces, for example, it's 37, so something will be silent here, and here I have some kind of activity, and then at 85, right? That's the next one. So it's around here, okay? Well, it shouldn't be like this. It should be. I'm not painting that very well, but it should be something like this. Right, so this is the basic thing I have. This is what I said. And now I convolve this with the response function of the bulb. So I assume that if this is the presentation of stimuli, so the bulb will look something like this, right? Something like this, or even more prolonged, okay, something like this. And the same here, right? It goes the right bit later and goes the same with the red ones, okay? So if the red ones are something like this, right? And same here. Now, my total signal may be something, I don't know. All right, I put it here. It can be something like this, right? So somehow, in this part, right, if the region I'm investigating right now, the voxel that I'm investigating now, is sensitive to one or more of these categories, okay, I should be able to model this kind of pattern with some kind of linear combination of these guys, okay, let's say, because I didn't, maybe it's not clear, but there is some overlap here, right, because of the continuous, the delay of the bulb, right, so let's say the blue one, let's make it even more clear, the blue one, right, is going like this. So here there's some kind of summation, so it's not very clear, but if, because the bulb is linear, like we talked last week, then I should be able to explain this to a certain amount by some kind of linear combination of these guys. So it may be, for example, that I put this, I give it a weight of 2.5, and I give this one a weight of, I don't know, 1.7, okay, or minus 0.2, okay? This is what I'm going to do with the GLM. It can work for 2 conditions. It can work for 20 conditions, okay? But the idea is the same. Try to maximize how much of the total signal I can explain by a linear combination of the predictors that I have. So a predictor won't look like this. It will look like this. So kind of hard to see, but what you see here is, for example, for the houses, let's say here I present a house, okay, so the convolved predictor with the HRF shows that at 3 hours after, for example, I'm starting to see a rise, so this is 0 up until now it's starting to see a rise, gradual rise. This is the peak, this is 1.06, and then it goes down, then there's some other long undershoot, you see some minuses here, and here we're back to baseline. So this is the modeling of the HRF, okay? And this is the object, okay? So the object appears before, it's one block before, so it starts here, and the house starts here. But you can see that it rises, and then it goes down, and then the undershoot is parallel to the onset, or basically the overshoot of the houses predictors. So we have some kind of overlapping predictors, and again, what we want to see is which combination of all predictors explain the overall signal best. Okay, I hope it will be even clearer in a couple of slides. So again, what we estimate are betas. Okay, these beta values are the modificator of the basic signal. Right? Again, some kind of convolution of the HRS with a binary signal, and this is what we try to model. And we play around with these betas. That's why you always hear about beta values when you talk about MRI. And if you have a timeline with n points, you have k conditions, so you have k beta values, okay? And you play again with the combination of those k beta values. In the most simple model we can think about is only 2 betas for 2 conditions. And this is your data. So your data, right, Y, this timeline, we talk about a single voxel, we're always in a single voxel. A single voxel has a timeline. The timeline is your model, okay, what we saw before with the text file, what we know we can model, times these beta, these weights that we play around, the model play around iteratively to find the optimal one, plus some error. We won't be able to model everything 100%. We have some error, and the idea is to minimize this error. Okay? So if this is the model, just put it. Yeah. So this is your data, and this is your model, right? So your model is basically what we said, the convolution of the binary predictors by some kind of multiplicator. And your error basically is the difference between what you calculate and what you observe, right? Okay. The idea is to minimize, I'm not going to go into the mathematics here. If you see some GLM basically or any kind of regression model, you know more or less what I'm talking about. But if not, just get the intuition, all right? I'm going to try to minimize the sum of square of the errors, okay, from the regression. And that minimization is done by constantly changing the beta values, okay, in an iterative process. Basically, in the end, it leads to some equation, and the notation that is more relevant for us is the notation that isolates the beta value. Okay, so what you can see here is that the beta value is some kind of a function that's dependent on the model. All right, some kind of mathematical operation that you do in the model, but basically it's the model and the observed data. Okay, why is the observed data? You have the observed data. The observed data, of course, is made of the model and the error, the residuals. So again, you play around until you get the optimal data. You can also think about this in terms of variance, but it's the same thing. Okay, and the idea is again that you have some variance, okay, in your model. But you have some variance in what you see, in the data you measure, and of course it's built from the variance of the model that you can predict and some unpredicted variable. And the idea is again, when you try to fit the model, you want this part, right, the variance of the error to be as small as you can, right? If you want, just mathematically, if you want to reach pi r square of 1, you want the denominator to be well, small. If you add this in the variance of the residual 0, basically you had a r square of 1, right? So the variance in the model would be equal to the variance of the observed data. Okay, so it's the same idea. All right. So going back to the timeline, you have some variance in the timeline, right? This is the 200 scans. You can put a simple boxcar that I showed you here, okay? This is your unexplained variance, okay? The yellow part or the residual error, okay? And you can see that if I just put a box there, I'm still far off from explaining the whole data. If I convolve the HRF with the boxcar, I get more explained data, of course, because it's now similar to the actual data that I observed. if I do some pre-processing and remove linear trend and stuff like other stuff, I get even closer. Okay, and the idea is always minimize the yellow parts. And this is true for one condition, but of course I usually have two or more conditions, and then I have to really, this is the part where I apply the GLM. Okay, up until now I just applied some kind of HRF and pre-processing to make it as close as I can to the data, but of course when I have two competing or two combining HRF from two different conditions, then I have to tease out which one contributes more or less to the overall signal. Before I go on, the idea is clear, more or less? Need some other questions or other ways showing it? Okay? So the idea, so next we're going to talk about how we derive contrast and do some statistics to understand what is really active and not active. But this is very important to understand. So usually, like I said, you can do some analysis on the data itself, but usually you work on the estimates. So either we're talking about univariate analysis or MVPA or all these kind of things that some of them you heard, some of them I'll just mention briefly today. Usually to go and work on the betas, okay, on estimates that you had. And this is assuming you had kind of a good educational guess or a good model, okay? You constructed the experiment in such a way that will reveal the voxels that for one condition are constantly different. Activation is constantly different between conditions. That will give you nice betas. If the region basically is noise in relation to a condition that you picked, so it can do something very important but has no relation to the three conditions that you picked, you won't be able to explain the observed signal in a good way.
When trying to minimize the data, do we also change the model that allows, or
what do you mean the model? The HRF is not changed.
No, not HRF, what we consider as predictors. Like
No,
can we
no, no, no. When you set, the only thing that you change is the relative height or amplitude of the response, but not the time. Not the time or the composition. The betas are just amplitude, relative amplitudes of
but we can like add.
you can do a different model, but right? But you can do, well, you can have other approaches that well, just try to see some like components of the data, like I showed before. But if you put in the condition, you can change the model. For example, if you put in the condition like houses and faces, okay, you model them with two predictors. You see regions that are responsive to houses or faces. You can also do houses and faces and put two different subcategories. Okay, for example, houses you know and just random houses, or faces of familiar people and unfamiliar faces, and you can first model them with two predictors, trying to see just houses and faces, and then you can model them with four predictors. Unfamiliar houses, unfamiliar faces, familiar houses, familiar faces. Maybe in some region you'll see more, you'll be able to explain or model your signal better. Okay, so
That's what I meant. It's okay that you don't do it like before, like a priori. It's okay.
no, it has to have, no, not exactly, because okay, not exactly. You have to think of the design what you want to do usually, because you have to have some matter of, for example, counterbalancing. For example, I don't want if I have four conditions, I don't want one to appear always after another. I want to have some kind of randomization because I don't want to have some kind of history effect on the trial. So that's one thing. You have, if you want to have more predictors, you have to have more repetitions because you're always dependent on the amount of data you have. So if you think you might want to redivide your categories instead of 2 to 6 or 8, you must think ahead that you have enough repetitions. So usually don't do that, but you can in theory. All right, let's continue for a couple more minutes, 5, 6 more minutes with the contrast, and then have a break. So you have some beta values, okay, and now these betas are basically, like I said, estimates of how responsive is that voxel for each and one of your conditions or your predictors, okay? Now you want to test explicitly some contrast, some difference in activity between these conditions and test it statistically, right? So do a t-test basically. Or yeah, some kind of statistical measurement. And for example, if you want to see which voxels in the brain respond more to faces than to hands, all right? So what you usually do, well, what you always do, but this is the notation usually, you build some contrast to be multiplied with your beta matrix. So you have one big matrix of betas, for each voxel, for each condition, you have a beta. Now we're talking within one voxel. And now you want, let's say the second one is faces, the second condition, the third one is hands. So you have a null, your hypothesis, the null hypothesis is basically that these two conditions are equal. All right? What you want to show is that they're not. Well, you want to find out in which voxel this is not true. So from that, if you say B2 equals B3, you can also say that B2 minus B3 equals 0. Okay, and this is why basically you multiply your betas by these values. Okay, so this is a contrast. This is how it would look in Brain Voyager or other software. And what you do is a t-test. The t-test is basically taking a signal and dividing it like noise. Again, I'm not gonna. We have only 2 hours of MRI introduction, so we're not gonna dive into that. Intuitively, you have some contrast. Again, this is your signal, basically what you modeled. Okay, you have some. You multiply it by the contrast, the relevant contrast that you're doing. Okay, so some of these will become zeros because they're not part of the contrast that you're doing now. You have some estimation of the standard error, which is an estimation of the noise you have in the system, and you can have t-statistics. Okay. So this is the basic idea. We'll see it in a minute on the brain. But you can, of course, do other stuff. Not well. You can do other kind of tests. Well, the same test, but in a different combination of contrast, basically. So you can say like which voxels respond more to faces than to everything else. That's also a valid question. And your contrast will look like this. Okay, and 4 is faces. And the idea is, again, your null hypothesis, right, is all of these together, right, divided by 4 equals B2. So this one equals everything else. This is the what you're trying to disprove, and we're changing it. You're left with these numbers, right? -1 in front of everything else, except your relevant condition. Okay, so this is basically what you're dealing with. So, applying the GLM for a certain voxel, you now have a beta value. Okay, there's some standard deviation, and dividing this by this, you get some t-value. You have a table, like any statistic. For the t-value, you have a t-value. Okay, and then you have some kind of statistic also for the specific contrast. Okay, so doing this contrast, let's say it was houses minus faces. So you take the betas of houses and faces, you get some value, you have some standard error of that, you can extract that from your data, and then you can have a t-value which is basically dividing this by this. Okay, I think it's even written here. Yes, it is. So let's go over it. You have some noise estimate for this contrast specifically. Again, you're getting it from the standard deviation of the relevant betas. You have the t, which is dividing the signal. Okay, beta, in this case, beta 1 minus beta 2. This minus this. You divide and get a t. From the t, you can calculate a p-value. This is just basic statistics. And this is the last slide before we take a break. You can also do some conjunction. Okay, this is just to tell you that you can do all kind of. This is somewhat. In the next half, we'll talk why this is somewhat limited analysis in some cases, but still you can do a lot of it. Okay, so you can ask which. Let's say if you. Okay, let's say if you say, and we finish with that. You tell me maybe what this is asking. This is saying basically. It's not hard, but what's the interpretation of this? So which conditions are these? Faces and hands. Okay, so this whole argument, what does it ask basically? What does it say? Which voxels
Are more active
are more active
in
in faces relative to hand? And that's this, yeah. What does it mean? You don't have to know, but guess, like intuitive guess. What does it mean that I have put this one and everything else in zero? Right, it's very simple, right? And it's just which voxels are visual responses, okay? Visual responsive when I show faces, okay? And this is similar, but it's very different, right? One is contrasting against. This is saying whenever I show face, these voxels are active, and this is active more than a different category. And why is that important? Why that is not enough sometimes? Think about it.
maybe understanding.
Yeah, exactly. There may be some difference between them that may be even significant, but it's all way under the responsiveness, like the baseline responsiveness. So might be true, but it's hard to interpret. Okay, let's have a break.
לא בעצמי. זה היה סיני. זה מצחיק ממש.
כן, בטח. לא, קודם כל, לא, לאו דווקא, אבל יש פה...
עשינו אנובה נגיד בסרט האנליסיס שלנו, ויצא לנו אקסטי ואליו ברמתה של E במינוס 93, כאילו קטן
כן, אז תשמעי, קודם כל אתה אמור לחזור על הדברים האלה. ב-MRI, נגיע לזה, יש בעיה רצינית של מוטות מקופלת. בדרך כלל לא נשאר חלקים דברים כאלה. אני אפילו לא יודע מה הדוגמה הזאת, אבל יש עוד משהו, זה דבר אחד באופן כללי. אוקיי? אני צריך לראות איפה הדוגמה הזאת. עוד משהו שאני יכול להגיד,
שספציפית... לא, לא סביר, משהו פה. אני מדברת על מה שהראיתי קודם.
כן, כן, מה שהראיתי קודם אני יודע, אבל... זה היה פה. כן, הוא גם מעגל את זה. לא, זה קורה, כי זה גם טיב על גבוה. אני אגיד לך איפה זה קורה הרבה פעמים. ווקסד, אתה עושה משהו מאוד פשוט. של שני גיבויים ויזואליים, שכל אחד אתה שם 20 שניות. זה קשה להאמין כמה זה רובסטי. אוקיי? כשאני מראה 15 שניות פרצופים ואז 15 שניות בתים, ב-FFA יהיה לי T-value יכול להיות של 15, כן? ה-T-value פה הוא 8. יכול להיות T-value של 15 בווקסים מסוימים. אני מניח שזה כבר מאיזה קורס של קורס. לא, זה בכלל לא מאצלנו, זה מאתר אחר שגנבנו, אז אני לא יודע בדיוק מה הם עשו פה, אבל לאזורים הוויזואליים זה יכול להיות. עוד פעם, אם את תקחי 500 ווקסלים באזור של ה-FFA, לא כולם יהיה להם T-value כזה, אבל האלה שהם רציניים זה יכול.
הם מראים את זה.
זה יכול להיות. זה יכול להיות.
לא יודעת, זה כדי שהשטח שלנו.
כן.
מעשית שאני אם זה בסדר, לשנות את המודל, כאילו עד שיתבאת כמה שיותר קטן, זה נשמע לי קצת כאילו ש...
לא, בסדר, אני אשלח לך דרך לשנות את המודל בצורה...
כאילו שאתה לאט לאט, כאילו אוקיי, זה קצת לשפר, אוקיי.
בסדר, אבל זה לשפר לך את ה... השאלה מה את עושה? השאלה מה את עושה עם זה? אם את עושה Houses versus Faces, וזה לא משהו, ואז את קוראת מאמר שיכול להיות שיש שם גם הבדל של זה לא Houses Faces, זה משהו אחר, את משנת המודל שלך לקרוא את לבדוק. בסדר גמור,
כאילו זה קצת, לא יודעת, כאילו, זה מזכיר לי את הקטע שאודי דיבר, שאודי אוהב לדבר עליו, של הכל פעם להוסיף עוד נבדק עד שאתה מקבל...
לא, אז שאלת, אז שאלו, עוד פעם, תלוי מה את עושה. אם יש לך דרך יותר אינטליגנטית, מה שחשבת, את צריכה לראות שדברים עדיין נכונים, כמו שאמרתי, בדרך כלל את לא תעשי. אבל, בסדר גמור לקחת אפילו לא רק לעשות מודל הזה, בסדר גמור לקחת את הדבר הזה, להסתכל פתאום אולי למדל את זה אחר בכלל, לא ב-GLM, אוקיי? כל עוד את לא לוקחת את התוצאות האלה ועושה איתם עוד משהו, זה כבר סיפור אחר. לוקחת את זה כמו בסקראץ', ממדלת את זה במקום בשני זה, וממדלת את זה עכשיו הפרדיקטור ל-G. כלומר, אין קאונטר בלנס, הם לא, כל מיני דברים שהם, ואין ביניהם איזו קורלציה מוזרה של... זה לא אותו דבר כמו לקחת את מה שקידעת ולעשות לו עוד איזה סטייק. elevation בכלל של ה-arousal system. מצד אחד יש elevation של המרצה, מצד אחד יש ירידה ב-arousal של כל ברור. ברור. זה בעיה.
בגלל שזה בחושך.
אין לי בעיה שאפשר לכבות ומקסימום עוד 20 דקות נדליק עוד פעם. עכשיו לכבות. אבל אם אני אתחיל להזיע אז אנחנו נחזיר את זה. לא רוצה להזיע למחשב. טוב. אוקיי. אז, היינו בקונטרסטים. זה מוח, אני בדיוק מנסה להסתכל להיזכר של מי הוא. Sorry. Yeah, I was talking with Shai and yeah, I moved to Hebrew. I'm just saying, I'm trying to remember whose brain is it. I'm not sure it's mine or Udi Zohar is, but one of us. And what you see here is, again, after you're doing some contrast, in this case faces greater than hands, maybe with a conjunction with just faces greater than 0, you get this classic activation clusters here in the SFA. So this is, we talked about it last week, this is the fusiform gyrus. We're looking now at the brain from the bottom, okay? This is the ventral region. And like I said, you reach this by extracting betas, okay, and then contrasting between the betas and finding significant differences. Now, you can see here some key, let's say, some kind of measurements. You see here the key, these are the time points, right? And you see some scale of t-value. You see some, this is QFDR, we'll talk about it in a second. You see some p-value, okay? And we said we're doing a GLM for each and every voxel, okay? And then we do the contrast for each and every voxel. So what should immediately pop out, like the problem here, we're doing statistics. How many voxels do we have in the human brain? Yeah. Yeah, we have around 100,000 voxels or something like that. Depends on the size and how much cortex we scan, and we have some kind of multiple comparison problem. Okay, very very large one, and we have to see how we deal with it. So what you see here is some kind of threshold that we can set, and you can see if we take this region here, we collectively check the average time course. So this is one time course for, I don't know, let's say 150, 300 voxels. Right, we see something like that, and this is responsive again to faces. You can see the rise here. If we raise the threshold, now the p-value is smaller here. The number of voxel is smaller, right? We get like a smaller cluster, but we get a slightly larger effect. I'm not sure you can see it here, but the signal stretches a bit. If we and notice that you have some activation here, you have some activation on the left side, right? You see it there. If we raise the threshold even higher, we can reach something like this, okay? So just half the size of the cluster, no activation on the other side, we reach astronomical p-values, well, very low p-values, very high t-values. This is 18, the t is 18, is quite high. Question is, how do we choose this? How do we know what we're doing here, basically? So, unfortunately, there is no one thing one solution here. You see now that this is actually a stricter, it's not a different threshold, but just a different contrast, right? So because it's a conjunction, so it may show us different clusters, but also using the same contrast that we had here, we can raise the threshold. Okay, so it can become a bit of arbitrary. And the result might differ because now we see only one unilateral activation. Here we see by lateral activation, and again this can be determined both by the threshold that we set and both by the and also by the exact contrast that we set. So if I again compare faces versus houses, or faces versus the scrambled version of those faces, or faces versus object, I'll get slightly different patterns of activation. There is no specific or right way to do this, by the way. So basically you should follow convention or do something that makes sense in the context of your research question. Okay, but you'll see some papers that define the face area by faces versus scrambled version, and sometimes it will be faces versus object. You can do something like faces versus multiple categories that will maybe give you a more reliable result, because you compare it not only to one category. But there's a lot of things to choose when you do this. So let me talk a bit about the multiple comparisons problem that we have. So as you know, if you did some statistic, you have two types of error. One that you miss some effects, okay? And the other one is that you have some false positives. Okay, some voxels in this case will show that they have significant difference, even though they don't really show this. It's type 1 error, type 2 error. I never can remember which one is which. Let's see if the region truly active no, so this is the false alarm, is type 1 error. Okay, and of course there's a balance. If you have set the threshold too high, right, you'll miss some real activation. If you set it too low, you might see something that is not really there. So, as in other fields of applications of statistics, you have some ways to correct that. The most straightforward is the Bonferroni family-wise error correction, and the idea is that you divide the p-values that you must obtain by the number of comparisons. In this case, you have to divide the p-values you need to obtain by, depends how many voxels you scan, but could be 100,000 here or 60,000 voxels, the N here. Okay, so we get something very, very, very strict. And usually, although you can do that, people don't use that. Let me see what it says here. Usually people don't do that because it is, you don't get a lot of false positive here, but you may lose a lot of real effects. Okay? There's some other alternatives, and again, there's no specific right or wrong here, but you should consider the pros and cons on each approach. One very popular way is using the false discovery rate, and again, intuitively, the difference here is that you estimate the probability of a false positive, okay, or something being significant by chance, as a proportion for the part of the actual voxels, not the whole set of voxels. Okay, what I mean. So P, if I scan 60,000 voxels, so with Bonferroni, P has to be divided by 60,000. But when I'm using the Q ratio with the FDR, let's say in the beginning, in the uncorrected, I have only 3,000 voxels around the brain that are found significantly different or significantly active. I need to divide my p-value or q value only by 3,000. Okay, so that is some kind of an adaptive measurement, and it's adaptive because it will change according to the absolute number of voxels that you found active. Okay, so it's very conservative when there is little activation. Okay. But it's less conservative when there's a lot of activation. And is that true? very conservative. When there is little activation, yeah, it's true. And just to get you familiarized with what you see here, so this is just uncorrected. This is just having a t-test without any correction, and you see a lot of activity around the brain that was supposedly significant. If you do the Bonferroni, you get something like this. So you left, again, with very, very distinct activation. If you do some QFDR, you get usually, typically, something in between. Okay, so some of these activations are still here, and some are not. So, what is best? There's no, again, no one absolute answer to that. If you can do, yeah, it's a good question. Sometimes you can do Bonferroni, it won't hurt you. The idea with QFDR, again, it will remove some unwanted noise usually, leaving the robust clusters intact, okay? So you want, let's see, this difference, this, this, okay? So something that is not very reliable, like these guys and other, will disappear, and some won't. Okay, so some kind of an intermediate step, but it's nice because it's adaptive. Now, we'll get in a minute to the fact that you, on top of that, usually do some group statistics. Okay, so this, again, is just doing the pre-processing, estimating the beta, making a contrast, and see which voxels survive the contrast in a single subject. Ultimately, if you're doing a classical analysis, you want to get like 16 of these subjects, and you do another second level analysis that see what voxels survive that that part. And usually, if you have some variability in those little clusters, they won't survive the group voxels. So you don't really have to worry about the group analysis. Just illustration. If you have some noise, this is just a model. You have some noise, right? You have some kind of, it's hard to see, but you have some kind of signal here. Okay, you create some kind of stimulus, let's say, with a signal in the center, and it's not a stimulus, it's just a model. Let's say these are voxels, and these are significant. Okay, this is real effect, and this is just noise. Okay, if you apply uncorrected, you don't correct for multiple comparisons, right? You get basically a lot of effect, but you get a lot of effects like false positives that are not really there. If you do the Bonferroni, right, you lose all the type 1 error, the false positive, but you get a lot of type 2 errors, so you don't see most of the actual effects as there. QFDR is some kind of in the middle again, all right? So you lose some of the actual data, but you don't gain a lot of false data, false positives. So again, this is just an illustration to show you what's there. Finally, you can do another thing, which is cluster size correction, and this correction doesn't raise the threshold. What it does, it exploits the fact that the data, okay, the voxels in the brain are actually, there's a spatial dependency between them, okay? They're not just a matrix that with independent components, and that's actually why, one of the reasons why Bonferroni here is much too strict, okay? There is an assumption that you don't always think about it, but if one voxel is very active in this condition, the neighboring voxel should be also active to a certain point, okay? And this is because, first of all, this is how the brain is organized, and also remember that the voxel resolution is something arbitrary that we decided, because this is what our magnet can do, right? Slice the brain to 3 by 3, but it doesn't mean that the real units are 3 millimeters. So, assuming that we have this spatial dependency between the voxels, this is much too strict, and you could do some cluster size correction, and this cluster size is some kind of Monte Carlo optimization process. Again, we're not going into that, but the idea is that you remove, okay, clusters that are under a certain size. You do a lot of iterations, okay, and clusters that don't survive through this iteration, okay, they don't get let's say, to be more than a certain, let's say, the minimum size of 10 voxels cluster. If doing this iteration, this small cluster that you see doesn't rise above the 10 voxels minimum, then you cut it off, okay? And then you are left with the real, robust, big, reliable clusters of activation. The other thing, which is last here, is using ROIs. ROIs, or region of interest, is the next mini subject I'm going to talk about. And before I get to that, just again, I didn't dive into the details, so we're not supposed to know exactly the little details inside each one of the approach, but the idea is clear, right? We have more or less 3 approaches. One is more strict than the other, and you should really think about what you're using. Region of interest. Region of interest is selecting, and we'll talk about how you do that, a region inside the brain, okay, in which you want to do further analysis, or you want to select parts of the brain and you want to see a specific contrast for those voxels that you selected, okay? First of all, why is it beneficial in this context? If you limit your analysis to a region of interest, right? That's very good. So we have something, and that's legit to do, of course, because your question of research basically changes a bit. So, well, at least your interpretation changes a bit, right? You say that according to, I don't know, some literature, you believe that this, or not literature, we talk about according to some definition that you have, you're looking for the effect in this region, so you may be more likely to find an effect because of the multiple comparison, but your assumption is different now, right? You're asking something a bit different. You don't ask where in the brain I have a differentiation between big houses and small houses. That's not what I'm asking. I'm asking inside the PTA, which I already know that is relevant for processing of houses, there, if that area shows a differentiation, okay? And of course, my chances to get there, get something effective there is greater, but the scope of my question, what I'm answering, is also more focused, okay? So you could do that. And it's a very, very useful tool, okay? And usually you do some kind of complementary analysis, you do some kind of overall whole brain analysis, and also region of interest analysis, and you can define these regions in 3 different ways. One is anatomical definition, right? So you will know that the motor cortex is somewhere, right, in front of the central sulcus. You can define the gyrus there and get the motor cortex. You can, let's see for the third one first, so you can get some kind of average mass of the cortex, okay, so it's less it's more roughly defined. It's less exact, but it can answer, again, if you don't have the data for one of these 2 methods to anatomical functionally define it for each subject, you can have the coordinates of where the PPA is usually, or the FFA is usually there, and you create some mass. And the middle option is the one that people usually use, and that is to functionally define the region of interest. And first I'll say what's the idea behind it, and then you tell me why it's a good approach. The idea is that I choose a task, okay, that I already know activates a region that does something. For example, I have the FFA, I show people faces and then houses. I see an area which is more active faces. I know that from literature, right? I use that activity to define the area, and now I'm asking my question. For example, do I see gender differences in that area? Okay? So, why do you think it's good to do this way? I could also, alternatively, by the way, right? I know it's in the fusiform area. I can slice the fusiform area from the brain and check my assumption within the fusiform gyrus boxes. So what's the pros and cons, and your thoughts about this? All right.
An area
So you have a more, I would say, one-to-one correspondence between your basically task, and that's a very good reason to do it. Although, in theory, it can also act against you because there might be some difference, okay? But you're right, in general, right? But there's another reason. This is one. And the second one has to do with the group analysis. You remember what we have, the variation, I don't remember if we talked about it, there's a considerable variation between the anatomical landmarks and basically, right, variation both in activation pattern and anatomical pattern in the brain. Okay, if I've taken an anatomical mask, I have to take, first of all, there's a difference between the anatomical parts from one person to another, but also there's some kind of also difference between the co-registration, okay? So, difference is double. I have the difference in quality in co-registration. When I co-registrated the functional data with anatomical data, I have some noise there, okay? So the co-registration is not 100% true, okay? So I have some variation there. On top of that, I have the variation that is inherent between persons. So then when I'm trying to talk about a region, I have a very varying region. It's going to be hard for me to pinpoint the actual activation across subjects. When I define for each subject the relevant set of voxels, okay, I'm now out of this mess basically, because I selected for each subject that region of interest, the family of voxels, the group of voxels that is relevant to my question or my task, and now I deal with that group of voxels for each and every subject, and they don't have to be the same voxels basically. All right, I don't have to relate to the same voxel like I do here. Okay, when I have this mask, average mask, I'm looking at the same voxel for each and every participant in my research. So it's a very good way both to limit your multiple comparison problem, focus your research questions on the area which you know are probably involved in what you research, in the price of losing some unexpected result somewhere in the brain, right? You lose that. And it's a very good way to overcome anatomical and functional differences between subjects. So this is just an example. Again, this was the paper that discovered the FFA back in '97. Today we use this kind of work just as a localizer to define the functional ROI. And what they did here is comparing, again, activation of faces versus object, faces versus scrambled images of the same faces, faces versus houses, and in a spining along the fusiform gyrus, clusters of activation. And what you can see, I hope that you can see it pretty, you can see that there is correspondence between the results, but there are some differences. Okay, and again, this is what I said, it really matters the stimuli you use. However, you see the correspondence between these three regions, okay, between these three comparisons. If you do some kind of conjunction between the three, you'll probably be left with these yellow, bright yellow bulbs here, right? So when you have more data, you can have more reliable voxels. But in any way, today you would do something like this to classically define your FFA. And this is usually done by very simple block design. You know what you're looking for. You put like 20 seconds of houses, 20 seconds of faces, 20 seconds of motion, 20 seconds of whatever to get a nice effect. So just to go over some classical regions in the visual system, but they're not only in the visual system. So in similar way, you can define the LO. So let's stop for a second to see what's here. So what you see here is the flattened cortex. This is the temporal part. This is the posterior part of the brain. This should be the dorsal part, okay, the parietal lobe, but it should be like this, and it's flattened like this, okay. This is the ventral, the bottom part, and you have here the early visual cortex, and then you have some functionally defined regions, okay. This is the FFA and the PPA on the fusiform gyrus, and here the PPA. You have the LO, which is sensitive to objects, again, versus from scrambled version. You have the MT region, which is sensitive to visual motion, again, versus some kind of other stimulus. They have the EDA that is sensitive to or participate in the processing of body parts, and so on. Okay, the idea is the same. You can, if you have a research question that really deals with some object representation, you would probably try to find first something all around the brain, and then, because you know this region is crucial for object processing, you'll define this region and dive in to check your specific research question there. Okay. I think I'm not going to talk about this. I'm just going to say in one sentence that just remember that, you probably won't, but I'll say it anyway, you have to have independent task when you're defining your region of interest. And that is because whatever result, in general, this is actually something important. So whatever result you have in general in science is always a combination of an effect and noise, okay? And the noise and the effect should be something that is reproducible, okay? To a certain point. If I do this experiment 5 times, I should get the same effect. The noise will be different, a bit. It will be random. Overall, it will be basically the same, but specifically have different distribution of the noise, okay? So whenever I get a result, for example, I define a region of interest, okay? That specific region of interest is a result of the real effect and some noise, okay? And if I use the same data then to analyze, I would sample the same noise, and that I shouldn't do. But we don't have time to that. Just remember that when you do this, you have a secondary task, okay, to define the region of interest. Then you go to the main research question, do your task, and check the effect of your main task within the region that you defined with a different, I'm going to skip that, with a different localizer. Okay? So the idea is clear, very simple. Okay. Last 15 minutes that I have, I want to talk a bit about what's going on now in fMRI research. Because the really interesting stuff has to do with the multivariate approaches that try to answer a more interesting question or account for a richer model of how we represent visual stimuli or any other stimuli in the brain. So up until now, we talked about which voxels are active to which condition, okay? Or in other words, which areas participate in that task or representing that stimulus, okay? And which areas don't, or which voxels don't. But you can ask more interesting question like, is the representation of something is modular? It has to do only in that cluster of voxel, or is it distributed across the brain? What's the effective resolution that this representation of, let's say, faces is kept? Is this some kind of population of voxels or population of neurons? If there's some kind of large-scale principles, like we know, for example, that receptor field size is getting bigger and bigger as you go further away in the visual stream. Are there any other large-scale principle in the brain? What is the relationship between the clusters that we find? Is some kind of network that's going on there? We can ask a question about what is the level of robustness across individuals, and some commonalities between mechanisms, let's say, and I gave here perception, memory, and imagery, but it can be anything else, okay? And the idea, well, we can do some of it with what we talked up until now, but recent methods test the patterns of multiple voxels in response to a certain stimulus or certain task condition. So if you have 9 voxels, you have some kind of activation pattern. Let's say the bright ones are less active, these are more active. Okay, you have 2 types of stimuli, and you check this box of 9 voxels, so you see overall a different pattern of activation in response to this kind of stimuli, and you take this pattern of activation, pattern of voxel, not only one voxel, and you test the correlations or the relationship between these patterns. But I want to just stress out that the values here are usually beta. So you do the GLM for each one of every voxel you have a beta value, basically, and then you look at the collection of beta values across the region, and it can tell you something about the presentation. So now we're not only talking about which region of voxels are more active, but we're talking about which areas hold relevant information, and we try to quantify and model that relevant information, and I'll show you, I have time to show you a couple of examples. So first, the idea. So we have a voxel, 3 by 3 millimeters, okay? And like I said, if you take 9 voxels, you have some different activity in a response to a certain stimulus in those 9 voxels, okay? If I take the categories we talked up until now, so if this is a region of interest, or just a subset of voxels in the brain, right? It will respond similarly, I guess, for each phase. You see some commonalities between those, but the actual patterns will be different. Now, the same goes for the houses. But key factor here is that if you average this, okay, average the region of interest, you get the same activation here and here, okay? So if you average all of these, you get this average activity and the same here, and you cannot differentiate if you reduce the region of interest to one level of activation for houses and faces, which people did up until 15 years ago. You cannot see any difference, but there is clear difference between these two groups, okay? And the idea here is that you take into account the specific patterns, and one of the key feature basically is if there is a category or there's a group of conditional stimuli that have something in common, okay, this will be reflected in higher correlation within that group of activation, okay? So these guys should be more similar to one another than to the group of the other stimuli and vice versa, okay? So this is the within category patterns or information. This is the between category, and you, if you assume, well, that's at least the logic, that if that hypothetical region of interest with 9 voxels is somehow differentiating or is processing information that is related to houses and faces, the within category similarity will be higher than the between category similarity. And when we're talking about similarity, we usually mean correlations, okay? So this is the basic idea. And now you're already starting to see that you have a much richer data, right? You have patterns, and you're not only talking about this voxel higher in one condition or the other, because it can be that voxel A is higher and voxel B is lower, but they're both parts of a vector, okay, or a pattern, and the fact that this voxel is higher for faces is important, but also the fact that this voxel is lower for faces is important, right? You're not thinking only the absolute height. So you can do the correlation, you can also do decoding, you probably heard of it. Again, if you take just 2 voxels to make it simple, you have here for the house high activation for voxel number 2 and low activation for voxel number 1, I think. Yes. And you plot this activation in some voxel space, which usually be like not 2 dimensions, but 200 dimensions. You're usually going to have like 100 and 200 voxels. And you can see that it has pretty high, let's say, activation in voxel 2, but lower activation in voxel 1. And you tag this as a house, okay? Now you get a face. You have an opposite pattern, right? And you have high activity in voxel 1, low activity in voxel 2. So in this space, this will be placed here. And again, we tag it. We put all these exemplars, okay, and the right tags into a classifier. Classifier is just machine learning algorithms that get the data and the correct responses and try to build a rule, a distinction rule out of it. Okay, so let's say this is the data that you collected. Okay, so what you will do is you take most of the data, you keep some part of the data later for testing, you'll try to build a rule for the decoder according to, let's say, 80% of the data, and then put the other 20% here and see if the decoder divides, see the distinction between the red and the green here correctly, if it learned a rule. So, in this training set, the decoder, which is a linear decoder, will probably put a rule somewhere here, because this rule catches most of the distinction between the houses and the faces. So voxel 2 is more responsive to houses, and voxel, when houses are presented, let's say, voxel 2 is more active and voxel 1 is less active. Okay? Then you put the trial set back, basically. Right? And now, because you have the boundary, you can see the classification that you get, and because before that the majority of red ones were below, so the bottom half is basically classified as houses, the upper half as spaces, and when you put the test data, you see that most, in this case, the classifier was built correctly, and this you have basically 75% correct classification. So this is the real data, and 3 out of 4 or 6 out of 8 cases were classified correctly. Okay, so this is the idea. So you're using the same data. Either you correlate between the patterns and see the amount of correlation that you have, okay, or you give some example to the classifier, try to set a rule, and then see the success rate that you have. And again, if this, the assumption is, if there is an information, okay, that is relevant to the distinction between, let's say, 2 categories, houses and faces in these voxels, so that should be reflected in a systematic way in which those exemplars are put here. So, specifically, if voxel 1 is always more active and voxel 2 is always less active when you show faces, okay, so if that is the case, you would be able to create some a reliable rule, and then when you have the test data, this rule will work. If this pattern of voxels, set of voxels, in our case 2 voxels, have nothing to do with representation of faces and houses, right? You get some random assignment here, and then, of course, when you do the test, you get some random success. Okay, and usually, of course, like I said, it's 100, 200 the voxel dimension. And in this is the idea that you can, again, give some some training sets. You basically collect a lot of data. In this case, the person sees these cards. You have some either a neural model, some kind of classifier. Basically, you train. You get usually it's not neural model, but a support vector machine. But the implementation doesn't matter. You train. You get some rule. You get some, hopefully, some generalization, and then in this example, well, this guy here sees a different set of rules. Hopefully, the classifier will be able to detect the pattern of seeing the card number 3 here. So when card number 3 is presented here, right, the classifier would say, okay, we'll get a brain activation, and we'll be able to say this guy saw card number 3 here, okay, because there was some kind of a generalized rule. Is that clear, more or less? Questions? From now on, it's just like 5 minutes that I can show you more slides, but we also can ask me a question about everything that was, so it's up to you. If you don't have a question, I'll show you one other thing, and with that we finish, which is the next step. Again, and this is another development in the last several years. So you can take a next step and not only ask which let's say, if the correlations within houses stimuli is higher than the correlation between categories, okay? You can try to quantify these correlations and try to create some metrics. And this is really interesting stuff, because people are developing tools to combine different branches of different approaches in basically system neuroscience. You can have a whole array, well, it's pretty hard here to see, but you can have a whole array of stimuli, okay? And you can correlate, in this case, the pattern of activity between the two patterns of activity that match two stimuli, okay? So I have this face, and I have another face, and I correlate the patterns between them, and I get a value, a high value. Then I have this face and the third face, and I correlate between them, and I have a certain value. I have a face and a house. I correlate between the patterns, I have the values. And I have this whole matrix of correlation, and from that I can derive nice metrics. So this is just some paper that was published in 2008. Let's concentrate at this part for a second. I just want to give a teaser about what you can do, okay? So here we have the whole set of stimuli, and you can see that it's divided into animate, inanimate, natural, artificial object, human body faces, non-human body faces, and plotting these are the similarities. So these are the opposite of correlations. It's 1 minus r. So what you can see here, first of all, that for example, this round object does not correlate very much with this red one. Okay, there, this red sign there. Because this is blue, so it means high correlation. Okay, and you can find these kind of structures in data, in representation, in the patterns that you research. So, for example, if we're talking about blue colors here are high correlation, basically high match. So you can see that you can correlate all these animate objects back with other animate objects. You get very high correlations. Okay, we could correlate the patterns elicited by presenting these objects with inanimate objects. You get very low correlations. So already you can see that in this part of the cortex that was measured here, there's a very distinct animate segregation. But this you can find with other approaches. But what you can do with that, you can take this very rich data that you have here, and you can visualize it in a very nice way. Here, for example, I want to show you a different one. I have only 1 minute. Let me show you this. So this is what we saw before. You can take these correlations and just plot them, some kind of metrics. Okay, so closer objects here have high correlation here. Okay, so some distribution of objects here. Okay, and it's distributed by the similarity of the patterns in the brain. Then you can ask people, all right, to just rate the similarity they think these objects are, the way they think they should be rated. Okay, this was done by a drag and drop thing, and this is basically what people have, the way people grouped. Okay, the correlate or the similarity between the same objects. Now you have something that some metrics of the behavioral part, let's say, behavioral measurement, okay, and you have some metrics of the neuronal or bold measurement, okay. This can be reversely plotted into this kind of matrix because you have a distance or similarity between each pair of objects, and what you have here is basically a way to compare, in this instance, between some kind of very intuitive behavioral metrics. People in this case just said, they were told, put the objects according to the similarity. And you can see how much this intuitive division of this object matches what's in this example, in the inferior temporal cortex. Okay, so in other words, how much of the variance here can be explained by this behavior. Okay, so that's one thing. You can also, instead of behavior, you can have here a model, a very complicated model. See the similarities in the model. Okay, plot them like this, and when you have the similarities of the same objects or stimuli in the brain, you can see how much your model matches the similarities in the brain. Okay, how much variance is explained by one and the other. Okay, this is a bit much for 10 minutes. This is just a primer. Okay, I just want you to get a sense of where the field is going these days. I will finish. First, you can ask me a question if you want, or after the class. We also have a whole course that deals with this stuff very thoroughly. I'm not sure if it will be next year or the year after, but stay tuned. And of course, you can contact me if some of this thing interests you. I'm always at the ANU at the scanner, and I'm available. So unless Shai wants to add something, questions for those of you who need to go, so go. If some of you need to ask questions, go ahead. And you don't have an exam, right? So no luck in the exam. You don't need that. Good luck with the assignment. Okay.
וואי, את לא מבינה, כי אני ממש לא הבנתי. זה היה קצת I didn't understand what I thought that no, like water running inside the wall or something weird. I don't know. And I looked at it like very suspiciously, you know, like am I imagining? And then, yeah, and then it was just, then I
Why mais comme toujours, ils demandent de tester les choses pour plusieurs valeurs, de paramètres. Donc au final, on se dit, bon, ok, on a plus de marge là-dessus que de faire faire des... C'est un peu répétitif, mais on trouve toujours des choses à dire.
Moi, honnêtement, j'ai jamais. Sérieusement, si m'avais dit il y a un truc, une vidéo avec cette image, j'aurais dit, c'est très bien. J'ai tout capté, c'est un... Ok, et apparemment, il y en a qui ont capté ça.
Ouais, je sais pas comment ils ont amené leur chose, si c'est dans la analyse en distance, ils ont vraiment envoyé un mail pour dire, bah, je vois pas du tout l'intérêt de la question. Peut-être nous, on l'a mal compris, peut-être qu'on l'a compris d'une manière...
Ce qui est sûr, c'est qu'on a...
C'est vrai que ça m'a un peu étonné qu'il y ait des gens il y a des gens qui ont écrit pour lui dire on voit pas l'intérêt de ça. Ou alors il a repoussé après, ça l'a fait réfléchir. Peut-être que sa première intention c'était de faire ça, et il y a des gens qui sont arrivés, que pour eux ça n'a pas d'intérêt, il y a réfléchi. Oui, effectivement,
C'est-à-dire qu'il avait juste dit, il y a une question sans intérêt, je pense qu'il ne pouvait même pas se dire laquelle c'est.
Ah, moi j'aurais dit que dans la partie analytique, entre la B et la C, on voit pas très bien la
Ok,
différence.
ouais.
Parce qu'en gros, c'est la B, c'est valeur exacte, c'est trouver un calcul, une approximation, et C, c'est trouver l'approximation.
Newman dans 2-3 heures.
Oui, oui, très bien, très bien.
Je sais pas, mais alors moi je sais pas par où commencer, si on fait des articles d'abord.
Moi, je sais ce que je vais faire, je pense.
Ce qui serait bien, quitte à en reparler après, si on a... Voilà, il y a deux choses. De toute façon, on va raconter. Oui, bien sûr. Et si on l'a lu, on sera capable de pointer du doigt sur sans avoir à
Ouais, alors on le lit. Bah voilà, c'est l'objectif de l'après-midi, c'est de le lire. Et on en discute. Bah, je sais pas combien de temps ça prend. Il faut peut-être en rediscuter d'abord avant de trouver la fin.
Bon, et on fait ça avant ce soir.
Et demain, t'es là ou pas?
Ouais, ouais.
Toute la journée ou pas?
Ah, toute la journée, moi je resterai juste... si mes spins...
Oui,
mais j'ai l'impression qu'il y a peu de chance parce que sinon il aurait une bonne. Et
I just going to the bathroom and go. Shiran, may I? No. So.
Sorry, Shannon.
Okay, thank you. I appreciate it.
on n'a rien d'autre à faire là en fait.
I want to
moi j'ai
start
plein d'articles
Ah,
à
ok.
lire.
of method and this one
Et puis,
and ours.
Don't worry.
non, toute la
Don't
journée.
No, really, yeah.
We'll take
Et
it.
après,
I
sinon,
want
il y a
Yeah, read ours.
no
Camille
because
qui...
in the next
c'est ça,
few
c'est ça.
2 weeks I'm not sure how it's
Et
going to
puis
be.
j'aimerais bien
Yeah, but we have a month for that.
faire une bonne présentation,
No,
mais
we
ce sera
have
en
a
discussion avec
physiology
les autres,
exam
mais pour
No, yeah,
les humains.
before.
I think I'll take it a
No, I
day.
also think it will be faster.
Okay, one day,
I'll just
9 to
read the
3.
papers and then.
But,
And what I want to do, I learn network.
yeah. Physiology, we should figure out a way to do it.
And sleep.
Okay, are you in physiology?
Yeah.
Did you start studying for the exam at all, or?
No, I just started.
I haven't.
When is the exam?
The 8th?
Yeah, that's the thing.
I started.
Did you get notes from anyone from last year, or?
Ja, nog.
Alright, send this in the chat real quick.
Ja, oh ja, ja. Ja, soms is dat.
If anyone has any notes from last year, please. You should find someone who takes notes on the computer.
Zanna, I guess.
Which one?
Zanna.
She has notes on the computer? You don't take computer notes in physio, I guess.
I guess,
Oh, you do?
You already
but
see
they're for my use only.
Okay.
Sorry, don't.
I just said you're an angel.
Shit, I don't let you go to the
The
bathroom.
weekend. No, but they're very partial.
Yeah.
Like
I had no
into one
They're not
amazing,
like,
no? Oh.
but they're not.
But they're not. Yeah, I guess it's probably the same more or less.
No, I mean, I think they're like a lot better.
But we're the same continuing drinking. Listening to music.
Yeah, if you
Bye.
listen to 1.5 Speed, have a good
תודה,
weekend.
Shabbat shalom. לקחת את הדברים שלי? כי אני בתחילת הדרך, לא? אני בתחילת הדרך כבר, כי אני צריכה להיות בדירה, כאילו קבעתי. מתי? אוקיי. אני אשים את זה המון שם בציפייה. כאילו זה שלי. אוי, שבעצם אני צריכה להתאחד עם מיליון דברים. אוי, פתאום קלטתי כי אני צריכה עם מלא דברים עכשיו. לא יודעת איך הדברים נכנסו לי לתיק בבוקר, עכשיו הם לא.
לא יודעת.
כן, נכון?
כאילו, תוך שימור הגודל או משהו.
וגם היה לי שנכנס פה קופסה אוכל, כמו שזה מעניין. אוי, לא.
מה?
אני חייבת ללכת ליפול פשוט.
תמצאי אותם.